everybody. My name is Fatma Kılınç Karzan. Today, together with my PhD student Alex Wan, we will present a tutorial on exactness in semidefinite programming, relaxations of quadratically constrained quadratic programs. We are interested in optimizing a quadratic function over a set defined by quadratic constraints. Throughout this tutorial, we will not make any convexity assumption on any of these quadratic functions. In fact, we will be interested in the nonconvex case, where at least one of the quadratic functions is nonconvex. We will have decision variables x in Rn and denote our quadratic functions by Qx. In this particular case, Qx involves the quadratic form determined by the matrix A, a linear component determined by the vector B, and possibly a constant C. In order to simplify our notation, we will represent this quadratic form in the form of a vector matrix vector product. And to further simplify our notation, in fact, we will denote this underlying matrix with the letter M. We will denote the matrix M generating our objective function specifically with M OP. And our constraints will have matrices M1 through MM, and we will use script M to denote the set of the matrices corresponding to our constraints. Based on this notation, the optimum objective value of our QCQP will be denoted by opt, and here we are minimizing our objective function over our domain, and our domain is referred as script X, and in particular in our domain, we have M less than or equal to type constraints. Although throughout the talk, in order to keep our notation simple, we will focus on the case where we have only less than or equal to type constraints. Our results apply to the case where we have equality type constraints as well. QCQPs are literally everywhere. They are used in optimization, statistics, machine learning. For example, classical problems like finding the maximum cut in a graph or maximum click of a graph have immediate QCQP formulations. These QCQPs appear in control, dynamical systems, in clustering, sparse regression, robust PCA. In general, any mixed binary integer program or any polynomial optimization problem can be reformulated as a QCQP with a small number of additional variables and/or constraints. The bottom line is that QCQPs are highly expressive, but also they are NP-hard in general because they contain these well-known classes of NP-hard problems. Let us take a look at our QCQP formulation again. In this talk, we will also study the epigraph associated with our QCQP. Here, we define a new variable t to move our objective function to the domain as a constraint. We will refer to the set defined by the objective and the constraints as the set script D. In this picture, the set D that lives in the X and T space is plotted in blue. Since now the objective function that we have is a linear function of our decision variables, optimizing this linear function over our domain script D is nothing but optimizing the same linear function over the convex hull of our domain. Here, the pink area is corresponding to the convex hull of our set. We have seen that QCQPs are in general nonconvex and NP-hard. Nevertheless, we have a strong tool, the semidefinite programming relaxation, that we can use to approximate QCQPs. Given a set of symmetric matrices script M, let us define the set script S, script M, as the set of n plus 1 times n plus 1 symmetric and positive semidefinite matrices satisfying the set of linear matrix inequalities, the inner product of M and Z less than or equal to 0 for all M in the script M set. Then the SDP relaxation of our QCQP is given by optimizing the linear objective function over the restriction that Z matrices should belong to script S, script M set. And the bottom right coordinate of the Z matrices should be exactly equal to 1. Note that this SDP relaxation is obtained by simply dropping the rank 1 requirement on the Z matrix. Throughout this talk, we will also examine the SDP epigraph set, script D SDP, which this set lives in the X and T space, and we have moved the objective function to our domain using the T variable. By definition, script D SDP set is a convex set, and it contains the convex of script D set, that is the epigraph of our QCQP set. As a result, we also know that the optimum objective value of our QCQP is lower bounded by the optimum objective value of our SDP relaxation. To sum up, we have seen that QCQPs are highly expressive, but NP hard in general. And we have a powerful and convenient tool given by the SDP relaxations to approximate them. Indeed, there is vast literature on the approximation guarantees of SDPs, dating back to the results on MaxCut by Gomez and Williamson, its generalization given in Nash-Strauss pi over 2 theorem, or matrix cube theorem, and so forth. In this talk, in contrast to these results, we will focus on exactness guarantees offered by the SDP relaxation. SDP objective value will match the QCQP objective value when we have a sequence of feasible and rank 1 SDP solutions converging to the optimum. One may wonder the complexity of the question of deciding whether the optimum objective values of a QCQP and its SDP relaxation match. A result by Laurent and Polyak from 1995 actually establishes that this question is NP hard to decide. Nevertheless, sufficient conditions that guarantee SDP exactness are of great interest. To this end, we will study 3 different notions of exactness. The first one is what we refer as the objective value exactness. This happens when the QCQP and its SDP relaxation have the same optimum values. Our second one is the convexal exactness, which is achieved when the convexal of the QCQP epigraph is given by the SDP epigraph exactly. Both of these exactness notions naturally exploit the given objective function of the QCQP. To complement these, we will also study the rank 1 generated property. This property provides exactness guarantees that are oblivious to the choice of the objective function. Without further ado, let me provide an outline for this tutorial talk. We will start by some preliminaries. In particular, we will recall the Lagrangian dual of the QCQP obtained by the aggregation of the defining inequalities. This will bring our focus to the set of convex Lagrange multipliers gamma and its role in defining the SDP relaxation. And this description will be the starting point for both the objective value and convexal exactness results that we will present. In the next section, we will work under the assumption that the set of convex Lagrange multipliers gamma is polyhedral and present sufficient conditions for objective value exactness and convexal exactness. Polyhedrality assumption on gamma is rather restrictive. So in the following section, we will drop this assumption and study general gamma and present objective value and convexal exactness results. In the next section, we will study the rank 1 generated property of conic subsets of the positive semidefinite cone. In particular, these conic subsets of positive semidefinite cone can be obtained by adding possibly infinitely many homogeneous linear matrix inequalities. We will observe that the rank 1 generated property implies objective value and convexal exactness in the original space, and we will present an ROG toolkit. Throughout these sections, we will complement our theoretical results with example applications and discuss other related work as well. Finally, we will wrap up with a brief list of takeaways and references. Alex will now take over, and he will present the Lagrangian dual and our framework for sufficient conditions on objective value and convexal exactness notions.
All right, so now we will move on to the main technical content of this tutorial. In this section, I will tell you two different ways of interpreting the SDP in terms of Lagrange duality and aggregation. This section and the following one are based on our math programming paper on the tightness of SDP relaxations of QCQPs. Recall we had the quadratic constraints Q1 through Qm. To simplify our notation later on, I'm going to define a vector-valued function, q of x, whose ith coordinate is the original ith constraint. We will also introduce some notation related to aggregation. Specifically, define A of gamma to be the symmetric matrix that is the AIs weighted by a dual vector gamma. Similarly, define B of gamma and C of gamma. To practice this notation, note that we can write the weighted sum of the quadratic constraints weighted by a dual vector gamma in Rm and evaluated at a point x as the inner product of gamma and the quadratic map q of x, or as the quadratic function in x with data A of gamma, B of gamma, and C of gamma. These three expressions are the same, but we may choose to write one over the other to emphasize that this expression is linear in gamma, as evident in the second expression, or quadratic in x, as evident in the third expression. All right, so with this notation, what we want to do is to construct valid inequalities for the convex hull of script D. For now, let's first try to construct valid inequalities for script D itself. Recall here that script D is the epigraph of the non-convex QCQP. So a natural family of valid inequalities on the non-convex epigraph is the set of inequalities that we can derive via aggregation. Specifically, given any non-negative scalar gamma objective and any non-negative m-dimensional vector gamma, we claim that the weighted combination of q objective of x minus t and q of x weighted by the dual vectors gamma objective and gamma is non-positive on all of script D. Indeed, this follows as q objective of x minus t and q of x are both non-positive on script D. As an illustration, we can pick any point in the non-negative orthant here to get a quadratic constraint in the x and t variables that holds on all of script D. Instead of doing that, however, I'm actually going to restrict myself to plotting dual vectors where the value of gamma objective is constrained to be equal to 1. When we do this, that is to say when we fix gamma objectives to be equal to 1, this consequence inequality here will correspond to an epigraph constraint. Q objective of x plus the inner product of gamma and q of x is at most t. As an example, picking the following point 1 gamma may lead to an epigraph constraint like the screen set here. And picking a different point 1 comma gamma prime naturally will give another valid epigraph constraint. Here, by valid, we mean that this epigraph constraint holds on all of script D. Or equivalently in this picture, that the green set contains the original non-convex QCQP epigraph depicted in blue. Note, however, that these green epigraph constraints are not necessarily valid for the convex hull of script D. In both examples here, the green set, which represents the consequence inequality that we derived via aggregation, is not a valid inequality for the pink set, which represents the convex hull of the QCQP epigraph. We will fix this on the next slide by restricting ourselves to considering only the convex constraints that we can achieve via aggregation. So, rewriting this expression again in terms of x, we see that the expression is convex exactly when the quadratic form in this expression, that is, gamma objective A objective plus A of gamma, is positive semidefinite. We'll collect all of these aggregation weights. Again, that is the vectors gamma objective comma gamma, which satisfy this assumption into a set which we will denote by the symbol capital gamma. In words, we will refer to capital gamma as the cone of convex Lagrange multipliers. Then, the same reasoning from the previous slide tells us that for any dual vector in capital gamma, that the quadratic constraint given by Lagrange aggregation holds on the convex hull of script D, the QCQP epigraph. Let's again illustrate this. Here, this figure illustrates what the intersection of capital gamma with the plane where gamma objective is equal to 1 might look like. Then, given any gamma in this yellow set, the green epigraph constraint corresponding to 1 comma gamma will then contain both the blue set script D as well as the pink set, which corresponds to the convex hull of script D. Again, this holds for any gamma in the yellow set so that we get a family of valid consequence inequalities on the convex hull of script D. All right, so the reason that we went into so much detail regarding aggregation is that aggregation explains exactly what the SDP relaxation of a QCQP does. Specifically, under a dual strict feasibility assumption, that is, under the assumption that there exists gamma star objective and gamma star such that the aggregated symmetric matrix here is positive definite, one can show that the projected SDP epigraph, DSDP, consists exactly of those points x, t, which satisfy all of the convex quadratic consequence inequalities that we can derive via aggregation. Note here that the constraint in the middle here is precisely the constraints that we derived via aggregation, and the assumption that gamma objective comma gamma lies in capital gamma is simply the fact that this constraint is convex in the x and t variables. So I should stop here and briefly mention that this dual strict feasibility assumption will be a standing assumption in the remainder of this talk. Okay, so coming back to this lemma, I'm going to give a quick depiction of what this lemma is saying visually. In order to do this succinctly, I'm going to assume for now that gamma happens to be polyhedral. Again, here I'm plotting the intersection of capital gamma with the plane corresponding to gamma objective is equal to 1. Next, we're going to observe that as the constraints that we are imposing in the x and t space are linear in gamma, it suffices to impose only the constraints corresponding to the extreme rays of capital gamma. In this figure, that will correspond to these 4 extreme points of the yellow set. Then, this lemma states that DSDP, or the projected SDP epigraph, is defined by these 4 quadratic constraints. As a side note, note that whenever gamma is polyhedral, that this lemma shows that DSDP, the projected SDP epigraph, is defined by finitely many convex quadratic constraints, so that it is in fact second-order cone representable. So we'll come back to this polyhedrality assumption later on in the talk, but for now, know that this assumption perhaps holds more often than you might expect at first. Specifically, it is clear that when the a sub i's are simultaneously diagonalizable, that capital gamma will be polyhedral. On the other hand, and perhaps surprisingly, the reverse implication does not hold in general, and capital gamma may be polyhedral even when the ai's are not simultaneously diagonalizable. Okay, so on the next slide, we're going to expand on this lemma on this slide a bit and actually give a third way of describing the projected SDP epigraph. So again, this is just a lemma copied from the previous slide. For the third interpretation, we will need to recall that the polar cone of capital gamma consists of all the linear forms which are non-positive on gamma. For example, if capital gamma looks like this orange set on the right, then capital gamma polar might look like this yellow set below, and it will be indicated with this circle. Then, by rearranging terms in our first description of DSCP, you may note that our constraint on the x and t variables simply say that the vector q objective of x minus t, comma q of x, must lie in gamma polar. Pictorially, a point x, comma t in the left image lies in DSDP, the green set, if and only if the image of x, comma t under the quadratic map, which maps it to q objective x minus t, comma q of x, lies in gamma polar, the yellow set on the right. All right, so now that we've covered some technical information on aggregation and duality, we can now get to some of the fun stuff and talk about sufficient conditions for exactness. In this next section, I will continue to assume that gamma is polyhedral, and we will briefly talk about how to remove this assumption in the section after that. So we will need two final definitions to state our sufficient conditions. Given a face f of gamma, we will say that f is definite if it contains a dual vector gamma objective comma gamma, such that the aggregated quadratic form is positive definite. Otherwise, we will say that f is semidefinite. We will often consider a specific face of capital gamma corresponding to a point in the projected SDP relaxation as follows. Given hat x comma hat t in DSDP, consider the face f of gamma exposed by the vector q objective hat x minus hat t, comma q of hat x. So I won't get into too much detail, but we can intuitively think of f as capturing the constraints that are tight at hat x comma hat t. To illustrate this, recall the figure below that we saw a few slides ago. This figure showed how to define DSDP in terms of capital gamma. Then, given a point hat x hat t in the projected SDP epigraph, so for example this yellow point here, we may ask which of the constraints defining DSDP are tight. In this particular example, that would correspond to the two constraints on the right. Then the face f exposed by q objective hat x minus hat t, comma q of hat x, would be the face of gamma generated by the right edge of the yellow set here. Okay, next, given a subset f of R1 plus m, we will define v of f to be the set of vectors such that the quadratic forms induced by the dual vectors in f each evaluate to 0. While the second definition is defined for all subsets, we will often use it for faces of gamma, and hence the choice of the symbol f in this definition. One thing to pay attention to here is that when f is a semi-definite face of gamma, the set v of f will actually be a linear subspace of dimension at least 1. This fact will be useful later on, but I will remind you of it wherever it is needed. Before we move on, I want to give you a very high-level motivation for why we might care about these definitions. So suppose we have a point hat x hat t in the projected SDP epigraph, and let f denote the face of gamma exposed by the image of hat x comma hat t under this quadratic map. Recall that f in a sense captures the set of constraints that are tight at hat x comma hat t. Then it turns out that v of f consists of exactly those vectors x prime, such that each of the aggregated quadratic functions corresponding to the aggregation weights in f behave linearly as we move beginning at hat x in the direction of x prime. That is, this expression at the bottom of the page behaves linearly in alpha as opposed to quadratically as we might first expect. All right, so now we can finally state our sufficient conditions. Our first sufficient condition states that if gamma is polyhedral, and that for every semi-definite face f of gamma, that this highlighted condition holds, then the optimizers of the QCQP and the optimizers of the SDP coincide. I'll come back to this middle highlighted condition in just a few seconds, but first note that this condition is stronger than objective value exactness. Okay, so coming back to this condition states that the projection of the set of linear forms corresponding to the intersection of a face f with the plane where gamma objective is equal to 1 onto the linear subspace v of f does not contain 0. So this condition probably looks quite mysterious, but I claim that it arises naturally due to the following proof strategy. At a very high level, the proof will work as follows. We will consider a point hat x comma hat t in the projected SDP epigraph and define f to be the face of gamma exposed by q objective hat x minus hat t, comma q of hat x. It's not too difficult to show that if f is definite, then in fact hat x comma hat t lies in the original QCQP epigraph. Next, if f is semi-definite, we will use the assumption to find a direction x prime to move in so that we may strictly decrease hat t and still remain in the projected SDP epigraph. This will then complete the proof, as given any optimizer of the projected SDP epigraph, we may deduce that the corresponding face f must be definite. This theorem is related to a similar result due to Buehrer and Ye for diagonal QCQPs. On the next slide, we will relax the assumptions of the current theorem to derive a sufficient condition for objective value exactness. Okay, so this next theorem continues to assume that gamma is polyhedral, but relaxes the middle highlighted assumption. Specifically, instead of asking that the projection of this set of linear forms does not contain 0, we will now assume that as a generating set for a cone, it does not generate all of V of f. In other words, this projection needs to be contained in some half space within V of f. While we won't go into the proof outline for this theorem, the main difference between the proof of this theorem and the proof of the previous theorem, and also the reason that we can change this middle assumption here, is that instead of trying to strictly decrease the objective value, it suffices to find a direction x prime, which simply does not increase the objective value. This theorem is related to a similar result due to Locatelli for diagonal QCQPs. Okay, so as an example application, we will apply this sufficient conditions to QCQPs with centered constraints and polyhedral gamma. Specifically, assume upfront that gamma is polyhedral and B1 through Bm are known to be equal to 0. Then note that B objective plus B of gamma is equal to 0 for any gamma. In particular, the cone that we are interested in is a cone generated by at most a single point. We deduce that this cone cannot be all of V of f, as V of f is a linear subspace with dimension at least 1. We conclude that objective value exactness holds in this setting. All right, so on the next slide, I'm going to strengthen this condition to derive a sufficient condition for convex Hall exactness. So again, suppose gamma is polyhedral, and this time assume that for every semidefinite face f of gamma, that the affine span of these projected linear forms is not all of V of f. One can show that under these assumptions, that convex Hall exactness holds. Again, we will not go into too much detail about this proof. However, to compare it to the proofs of the previous sufficient conditions, the main difference this time is that instead of simply keeping track of a single point hat x comma hat t and trying to move in a direction with a decreasing hat t value, the proof strategy for convex Hall exactness will require us to find directions that allow us to perturb hat x hat t in both directions. That is, we need to be able to find convex decompositions within DSDP. All right, so unfortunately, that's all I will be able to say today about these proofs. Let's move on now to apply this theorem to an example application. So as an example, this theorem allows us to handle QCQPs with polyhedral gamma and large amounts of symmetry. Specifically, suppose gamma is polyhedral, A objective and each of the AIs are Kronecker products of the K by K identity matrix and a smaller matrix, which I've denoted here by blackboard A objective and blackboard A sub I. The setup occurs, for example, in the Buehrer-Monteiro method for solving SDPs. Note that under this assumption, we in fact have that for every semidefinite face f of gamma, that V of f is a linear subspace of dimension at least k. And this follows from the Kronecker product structure that we assumed. Then we can derive sufficient conditions for convex Hall exactness by bounding the affine dimension of the projective linear forms. Two obvious ways to bound this affine dimension are in terms of the affine dimension of B of gamma, as gamma ranges over all of Rm, or in terms of the affine dimension of f intersected with the plane where gamma objective is equal to 1. These two quantities can then be bounded as either the number of non-zero B sub i's or m-1 respectively. Taking the minimum of these two quantities, we then get the following bound on the affine dimension. Then, as long as k is at least this bound plus 1, we can conclude that convex Hall exactness holds. Okay, we will wrap up this section by saying that the same theorem can also be used to recover a number of results related to the generalized trust region subproblem, QCQPs with spherical constraints, as well as quadratic matrix programs with polyhedral gamma. All right, so in my remaining time, I will tell you briefly about ways to get rid of the polyhedrality assumption. This section is based on a preprint titled A Geometric View of SDP Exactness in QCQPs and its Applications. So first, it is worth mentioning that the polyhedrality assumption is quite substantial, and that even very simple sets can have non-polyhedral gamma. For example, this assumption may be violated in the presence of a big M constraint. Recall that such constraints are used to model logical relations between binary and continuous variables. For example, this three-dimensional set here, where t is at least x squared, y is a binary variable, and x must be equal to 0 whenever y is off, can be expressed using the quadratic constraints on the right. A quick computation then shows that the set on the right has a gamma, which is a rotated second order cone. And although the second order cone is quite simple, it is not polyhedral. So we will attempt to extend our framework to handle non-polyhedral gamma. And for now, we will restrict ourselves to considering only convex Hull exactness. One way of phrasing our previous proof strategy for convex Hull exactness was that given a hat x and hat t in the projected SDP epigraph, but not in the QCQP epigraph, we constructed a direction x prime t prime such that we could perturb hat x comma hat t by small amounts in the direction x prime comma t prime, both positive and negative amounts, and still remain in the projected SDP epigraph. Our goal now is to do the same thing in the non-polyhedral setting and to do so in a systematic manner. In order to do this, we will need to re-examine the face f that commonly arose in our previous analysis. Recall that in the polyhedral setting, we considered the face f of gamma exposed by the vector q objective hat x minus hat t, comma q of hat x. In this picture, this vector might look like this yellow point here, and f would then correspond to this one-dimensional face of gamma in the top half of this picture. One thing that we haven't yet called explicit attention to is the fact that the analysis in the polyhedral setting was actually performed with span f and not f itself. Okay, so this quantity span f, although it was the correct object to look at in the polyhedral setting, turns out to not carry enough information in the general setting. It turns out that the correct object to be considering is in the general setting has to do with the polar cone of gamma. Specifically, define g of hat x hat t to be the minimal face of gamma polar containing the vector q objective hat x minus hat t, comma q of hat x. In this example, that would be this one-dimensional face of gamma polar in the bottom half of this picture. Then it turns out that much of our analysis can be extended, given enough care, if we replace span of f with the orthogonal complement of f. Our saving grace previously was that the span of f and g perp can be shown to coincide whenever gamma is polyhedral, but in general that this will not be the case. Here in this picture, g perp, the red plane, contains additional points tangent to gamma at f. All right, so replacing span of f with g perp in our previous analysis and extending some of those ideas, we can then identify a particular subset of directions, x prime t prime, such that small enough perturbations of hat x hat t in these directions remains in DSDP. This then gives us the following slightly messy sufficient condition for convex Hull exactness. While I won't go into too much detail about it, I will say that the proof ideas are very similar to those of the polyhedral setting, with the main difference being working with gperp instead of span of f, and all the additional complications that arise because of it. One interesting result of this process is that we can prove that when gamma polar is spatially exposed, that is, when each of the faces of gamma polar is given by the intersection of gamma polar with some supporting hyperplane, we can prove that this procedure actually identifies all of the directions such that small perturbations remain inside DSDP. That is, opposed to just a subset as indicated in the first bullet. In particular, we can prove that the sufficient condition for convex Hull exactness in this theorem is actually also a necessary condition in this special setting. So with this new sufficient condition, we have extended our framework to additionally handle sets with big M constraints, as well as general quadratic matrix programs without the explicit polyhedrality assumption. All right, finally, to conclude. In these two sections, we saw a number of sufficient conditions for different definitions of exactness in both the polyhedral and general gamma settings. In the polyhedral setting, these conditions depended on the projection of the linear forms associated with the intersection of f with the plane where gamma objective is equal to 1 onto the linear subspace V of f. In that portion of the talk, we considered sets such as the cone or affine space generated by this set. We then saw a generalization of some of the ideas from the polyhedral setting to the setting of general gamma for convex Hull exactness. In that section, we further claimed that the sufficient condition we provided is also necessary in the special case where the polar cone of gamma is facially exposed. Finally, throughout these two subsections, We saw applications of these sufficient conditions to a number of settings such as QCQPs with centered constraints, as well as QCQPs with large amounts of symmetry. Additional applications of our sufficient conditions can be found in the tutorial. All right, I will now pass the stage back to Fatma, who will tell you about exactness conditions beyond convex hull exactness, and specifically the ROG property that we alluded to at the beginning of this tutorial.
In this last part of the tutorial, we will focus on our last exactness notion, namely the rank 1 generated, or ROG property. After discussing its characterizations and applications, we will examine some sufficient conditions for a set to possess the ROG property and establish the necessity of these conditions in one specific case. The main reference for this work is this paper, which is joint work with Alex and CJ Argue from CMU Math. In this part, we will be focusing on the set script S script M, defined by the intersection of the positive semidefinite cone and a possibly infinite system of linear matrix inequalities. We formally define the ROG property as follows. A closed convex cone S that's subset of the positive semidefinite cone is rank 1 generated if it is exactly the convex hull of its rank 1 matrices. Indeed, this is exactly the same as requiring all of the extreme rays of S to be generated by rank 1 matrices. The rank 1 generatedness is a set property. We may compare the ROG property of a closed conic subset of the positive semidefinite cone with the integrality property of a polytope. In both cases, the property states that the convex set in question is the convex hull of a non-convex set of interest. As an immediate example, the positive semidefinite cone itself is rank 1 generated. A more interesting example is given by S lemma, which states that adding a single homogeneous linear matrix inequality to the positive semidefinite cone results in a rank 1 generated set again. In this research, we are interested in understanding, given a set of symmetric matrices, script M, when is the set, the resulting set script S script M is rank 1 generated. Recall that we can represent any QCQP as the optimization over specific rank 1 matrices from script S script M set, where their bottom right entry is set to be 1. The corresponding SDP relaxation is obtained by dropping the non-convex rank 1 requirement. Therefore, the SDP domain is the intersection of a set of the form SM and a single affine hyperplane. This original SDP relaxation hints us that through the rank 1 generated property of script S script M, we can provide some exactness guarantees. In particular, for QCQPs with only homogeneous constraints, under the dual strict feasibility assumption, we can show that script S script M is rank 1 generated if and only if the SDP relaxation is tight for every choice of the objective function. In the case of non-homogeneous QCQPs, we observe that the rank 1 generated property of script S script M ensures that for all objective functions and inhomogeneous constraints, the SDP relaxation is tight. Moreover, under minor dual strict feasibility assumptions, ROG property implies that exact convex hull characterizations of the QCQP domain or the closed convex hull of the QCQP epigraph set is given by the projected SDP domain or the closure of the associated SDP epigraphical set. These convex hull exactness results allow us to recover, for example, convex hull characterizations associated with generalized truss region problem, or the simple mixed binary set that was discussed in the previous section. To summarize, we observed that the rank 1 generated property under minor additional conditions provides SDP objective value exactness and convex hull exactness guarantees. While we do not have time today to discuss these, we show in the tutorial that ROG property allows us to derive natural S-lemma variants involving multiple quadratic forms, and also to derive objective value exactness results for the problem of minimizing a ratio of quadratic functions over a quadratically constrained domain. While the first form of ROG results dates back to the celebrated S-lemma, the literature on ROG property is relatively recent and much more limited. Indeed, this property until recently had only been studied incidentally to other research questions, such as truss region problem and its variants, or positive semidefinite matrix completion, or cones obtained by adding finitely many homogeneous linear matrix equations and the resulting algebraic geometry-based connections with applications in statistics. In contrast to these, today we will examine ROG property for general cones with possibly infinitely many linear matrix inequalities, and this generality will allow us to handle sets defined by conic constraints as well. To recap, given script m and the associated script s script m, we are interested in identifying sufficient or necessary conditions on script m that guarantee that script s script m is ROG. Given a set script m, we will quickly switch from studying script s script m to sets defined by linear matrix equations of the form script t script m. Indeed, we will see that script t script m is simpler to analyze than script s. When non-empty, script t is a face of script s, and it's easy to establish that script s is ROG if and only if every one of its faces is ROG. Therefore, script s being ROG implies that script t is also ROG. But the reverse implication does not hold in general. When m is finite, we can lift inequalities in script s to obtain a set of the form script t. But the ROG property is not necessarily preserved with this operation. In our written tutorial document, we present tools relating ROG properties of script s and script t through their facial structures. These tools are particularly instrumental when analyzing spectahedral sets defined by finitely many linear matrix inequalities or linear matrix equations. In the case of a single LMI, S-lemma implies that script S and script T are both ROG, regardless of the choice of matrix M defining the LMI or LME. However, this is no longer true in the case of two LMIs or LMEs. For example, in this figure, we observe that two LMIs defining this conic subset of 2 by 2 positive semidefinite matrices is not rank 1 generated. Indeed, the identity matrix, which has rank 2, spans an extreme ray of this set. On the other hand, when two LMIs are such that they are non-interacting, that is, the associated linear matrix equations only interact on a single, possibly trivial face of the positive semidefinite cone, and on this space, they impose the same possibly trivial constraint, then the resulting set is rank 1 generated. This lemma gives an immediate characterization for a pair of linear matrix inequalities to be non-interacting, as the condition that there is a non-trivial combination of the underlying matrices that's positive semidefinite. This then gives our first sufficient condition for ROG property. In fact, this sufficient condition can easily be extended to handle multiple linear matrix inequalities. It requires that every pair of these matrices defining LMIs is non-interacting. In such a case, both the script T and the script S sets are rank 1 generated. The ROG property of a set is intimately connected to the existence of non-zero solutions of underlying systems of quadratic inequality and/or equality constraints. And we examine the set script E defined for the set of matrices script M defining script S and any matrix Z in the set script S. In particular, S is ROG if and only if for every non-zero matrix Z from script S set, we can show that range of Z intersected with script E set is non-trivial. A similar characterization is also possible for the script T set, but this time we seek the existence of non-trivial vectors in the intersection of range of Z and script N set. Here, script N set is indeed a variety. That is, it is the set of solutions to the homogeneous system of quadratic equations defined by script M. It's easy to note that for any Z in script S set, the associated script E set contains the script N set. Thus, if we build a sufficient condition based on script N set, then we will guarantee that both the script T and the script S sets are rank 1 generated. Moreover, it suffices to check this condition for only matrices Z of rank at least 2. To summarize, a sufficient condition for both script S and script T sets to be rank 1 generated is given by the requirement that for all Z in script T with rank at least 2, the range of Z intersected with script N set is non-trivial. Since this requirement is for matrices Z with rank at least 2, their range will be at least 2-dimensional subspaces. Consequently, by a dimension counting argument, we deduce that when script N contains a homogeneous hyperplane, such as A perp, then this sufficient condition for our G will automatically be satisfied. Hence, given script M, we would like to know when script N contains a homogeneous hyperplane. Note that script N, script M is obtained as the intersection of script N sets of individual matrices M in script M. Thus, we can seek out the characterization in the simplest case of when script M is just a single matrix M. In general, we cannot expect script N M contains a hyperplane. For example, this picture corresponds to script N set for a rank 3 indefinite matrix, and clearly it does not contain a hyperplane. However, we have a simple characterization of when a script N set contains a hyperplane. This in particular happens if and only if M is a specific rank 2 indefinite matrix of the form AB transpose plus BA transpose. In fact, in such a case, it contains 2 hyperplanes. One is A perp and the other is B perp. This result then implies that for any vector A and any set of vectors from script B, both of the sets script S and script T defined by the particular set of rank 2 matrices parameterized through B are rank 1 generated. By interpreting the vectors in B as generators of a dual con, we observe that the constraints in script S can be written as a single conic constraint of the form ZA in con K. Hence, we deduce that adding the conic constraint ZA in K, where K is any closed convex con, is rank 1 generated. Conic constraints of this form are of interest when studying variance of truss region subproblem and the related second-order con reformulation linearization strengthening of their SDP relaxations. Overall, these sufficient conditions we have presented so far, with a little more work, allows us to recover a number of non-ROG sets from the literature. Let me close by summarizing the case of 2 linear matrix inequalities. We have identified the following 2 sufficient conditions for the ROG property. The first condition covers the simple case of non-interacting LMIs. The second condition covers the important case when the 2 LMIs interact in a non-trivial manner inside the positive semidefinite cone. Indeed, this is the case where the set script T is the convex hollow union of two faces of the positive semidefinite cone with a particular intersection structure. Through a non-trivial analysis that crucially relies on Dean's theorem and the consequence of Bezos' theorem from algebraic geometry, we can show that in the case of two LMIs, these two conditions are not only sufficient, but also necessary. This then gives a complete characterization of the ROG property in the case of two LMIs and generalizes the only other well-known characterization of the ROG property in the case of a single LMI, which was given by S. Lemon. Finally, I would like to comment that both directions of this theorem admit small certificates. When S is rank 1 generated, we can certify this by either providing non-trivial aggregation weights resulting in a positive semidefinite matrix, or doing a spectral decomposition of the matrices M1 and M2 and exposing their specific rank 2 structure desired in the second part of the condition. When script S is not rank 1 generated, presenting a positive definite matrix in script T will certify that condition 1 fails. This is through Gordon-Stemke theorem. Also, if the rank of either one of the matrices M1 or M2 is greater than or equal to 3, then the corresponding spectral decomposition of the matrix will certify that condition 2 fails. Otherwise, both M1 and M2 are indefinite rank 2 matrices, and writing specific indefinite characterization of these matrices and identifying the 4 distinct vectors involved will indeed provide the desired certificate that shows that condition 2 fails. We have seen that the rank 1 generated property implies close convexal exactness for any objective function. Although we did not have time to discuss this, we know that a ROG property plays a role in a number of other applications as well. Today, we discussed a few tools from our ROG toolkit. Please check the tutorial and our underlying paper for more tools, such as operations preserving ROG property, facial implications of ROG property, etc. We also discussed sufficient conditions for ROG property based on non-interacting LMIs or solutions to quadratic systems. Finally, we saw that these two sufficient conditions are indeed necessary in the case of two LMIs and provide a complete characterization of the ROG property. Let me close with a few takeaway messages from this tutorial. QCQPs are highly expressive. Indeed, they are everywhere, but they are also NP-hard. So we rely on a convenient tool, the SDP relaxation. In the first part of this tutorial, we studied the epigraph set of the QCQP, namely the script D set, along with the associated SDP epigraph. And we identified sufficient conditions for objective value exactness and convexal exactness of the SDP relaxation. In particular, we presented these sufficient conditions first for the case when the set of Lagrange multipliers gamma is polyhedral, and then later on, we lifted this polyhedrality assumption. Under a technical assumption, in the case of general gamma, we also observed the necessity of the sufficient condition. In the last part of the tutorial, we studied the lifted space of the positive semidefinite matrices and examined the set script S, script M. In this space, we focused on the ROG property, which presents a beautiful geometric view on subsets of the positive semidefinite cone. And we developed a toolset on ROG. We have seen that under minor dual feasibility assumptions, ROG implies SDP objective value exactness and convexal exactness guarantees in the original space. It also leads to variance of S lemma and so forth. We have seen a number of sufficient conditions for ROG property, and we showed that these conditions are also necessary in the case of two LMIs. Thank you for listening to our tutorial. We hope that you enjoyed our tutorial and are inspired to think further about questions related to SDP exactness. If you are interested in further details, please do not hesitate to reach out to us or read our tutorial and/or the corresponding papers this tutorial is based on. Finally, here is a list of the references that we have cited in this tutorial. Goodbye.